Welcome to this explainer. Today, we're jumping straight into decoding a classic navigational puzzle, finding literally any angle on the coordinate plane. If you've ever felt a bit dizzy looking at massive or negative degrees, hey, you're in the right place. We're going to build a rock-solid toolkit to confidently map out our mathematical universe. Just to get us in the right mindset, there's this fantastic quote from the ancient astronomer Ptolemy: "When I trace at my pleasure the windings to and fro of the heavenly bodies, I no longer touch the earth with my feet." He felt this profound sense of cosmic wonder when tracking the stars, and honestly, that's exactly what trigonometry allows us to do. We're taking that exact sense of wonder and translating it into the precise mathematical mechanics of tracing angles on a grid. So here's our roadmap for today. 1. Mapping the standard position. 2. Locating the basic angles. 3. Taming angles beyond 360. 4. Decoding tricky negative angles. And 5. Why angle tracking actually matters. Let's get into it. Section 1. Mapping the standard position, the starting line. You really can't chart a course without a starting line, right? Think of the standard position as the absolute zero of our mathematical compass. It's the baseline for every single angle we're going to graph today. The vertex is locked right there at the origin, and that initial side is resting perfectly flat on the positive x-axis, pointing straight to the right. And because of that starting point, we can chop our 360-degree circle into 4 distinct trackable zones, the quadrants. Starting from standard position and moving counterclockwise, quadrant 1 goes up to 90 degrees, quadrant 2 takes us to 180, quadrant 3 to 70, and finally quadrant 4 brings us full circle right back to 360. Section 2. Locating the basic angles, the first coordinates. Now, let's take this map and directly apply it to question 1 from chapter 3.1. We're going to figure out exactly which quadrant specific angles land in. We'll start with a super easy target, a 25-degree anti-clockwise sweep. Just visualizing our quadrant map, where do you think this one goes? Well, by just rotating a slight amount from that standard position, we lock in our very first solution. Because 25 degrees sits comfortably between 0 and 90, it hasn't quite reached that vertical y-axis yet, so it firmly belongs in quadrant I. Pretty simple, right? Okay, next up, let's tackle a much larger but still basic angle, 328 degrees. We're sweeping almost all the way around the circle this time. The really crucial point here is just knowing those basic quadrant boundaries. Because 328 is greater than 270, but hasn't quite hit that full 360 mark, it drops right into quadrant IV. Once you've mastered those boundaries, angles up to 360 are an absolute breeze. Section 3. Taming angles beyond 360, the spin cycle. So what exactly happens when the numbers just go completely off the charts? Take 825 degrees, for example. I mean, it sounds like an extreme skateboarding trick, but in trigonometry, it literally just means you're spinning around the origin more than twice. We just need a way to figure out where we actually park when all that spinning stops. To conquer massive numbers like this, we use the concept of coterminal angles to basically strip away the excess full rotations. The idea is simple. If you spin in a full circle, you end up exactly where you started. By subtracting multiples of 360 degrees, we can find a much simpler equivalent angle that shares the exact same resting place or terminal side. Let's actually walk through the steps for 825 degrees. First off, how many full 360-degree rotations can fit into 825? That'd be 2 full rotations, which gives us 720 degrees. Subtracting that 720 from 825 leaves us with a remainder of 105 degrees. And since 105 sits nicely between 90 and 180, we can easily pinpoint its final resting place right in quadrant 2. Section 4. Decoding tricky negative angles, going in reverse. Now, we've got to flip the script entirely. Notice how a negative sign simply acts like a steering wheel, throwing our rotation straight into reverse. While positive angles spin anti-clockwise, negative angles dictate that we spin clockwise, dropping down from that positive x-axis starting line. So if we take an angle like negative 55 degrees, we obviously don't go up into quadrant 1. Instead, rewinding just 55 degrees downwards gives us a super quick answer. The number is small enough that we don't cross any major axis lines, dropping us immediately below the x-axis right into quadrant 4. Let's test this reverse logic with a slightly bigger number. Where exactly does negative 230 degrees land? I want you to try visualizing this with me for a second. You're starting at 0, spinning backward past the bottom of the graph. You hit -90, then -180, keep going. Where do you eventually stop? By just breaking down that backward sweep, we effortlessly decode the whole thing. Moving clockwise, we cross all the way through quadrant IV, then pass -180 degrees as we sweep through quadrant 3. To hit -230, we just need to go 50 degrees further. That pushes us right over the line, securing our final angle firmly in quadrant 2. Section 5. Why angle tracking matters. The real-world application. Okay, let's summarize all this hard work. This is the highly satisfying payoff, a complete cheat sheet for all 5 parts of Chapter 3.1. Question 1. Fully conquered using our Navigator's Toolkit. We tracked standard anti-clockwise sweeps for 25 and 328 degrees. We stripped down massive spins using coterminal math for 825. And we shifted into reverse for our negative angles, -55 and -230. We've literally mapped them all perfectly. But remember, we aren't just solving abstract textbook math here. By tracking these specific rotations on a coordinate plane, we're actually learning the foundational language that scientists use to track light waves, to understand the behavior of sound, and even map the predictable winding orbits of planets, exactly as Ptolemy envisioned all those years ago. It all starts with a simple standard position and just tracking the spin. But seriously, think about the profound power of trigonometry here. If mapping degrees on a circle can unlock the secrets of light waves and planetary motion, what other invisible natural patterns are out there just waiting for you to decode them? Keep exploring and keep mapping your universe.